Well, hello, ladies and gentlemen. Welcome back to Math 1 Honors version. This is technically the last section in Unit 7. Finally, we're here. Hope remote education's going okay for you. We're probably going to slow this down a little bit and stretch this out, this section out over the course of a week or so. Now, at this point, this is sort of a quick little overview of where we're headed with this. And at this point, we've already proven triangles are congruent. You found several different ways to do that, sort of thinking incrementally. Just to put this into the big picture, you could take everything we're doing and put it onto a graph. You know, whether you put triangles on a graph or you put equations on a graph, lines, curves, anything, you put them on a graph. And then you can use what we're talking about with congruence to prove different things. For example, if you had two triangles that were congruent, because they were, you know, side angle side or side side side, you could prove their areas are the same. By the same token, you can do that with curves. So you'll see this sort of triangular shape here on this other example. Technically, it's not a triangle because this is a curve and that's a curve, but it's the same concept as when you find area of a triangle over here. You could find the equation of one of these lines, which I think I did over here, y equals 3/4 x minus 2.5. Obviously, the slope is 3/4. You could find that slope, you could find the y-intercept, and you could integrate this equation to find the area. And if you consider all three equations and all three of these equations, those equations are going to have some sort of equivalence in terms of area. Showing the same thing over here, trying to bumping that up a notch. You know, imagine doing that with curves. That's where this really becomes powerful. You do this with curves, and it's all through this concept of integration, which is related to this CPCTC concept about congruent triangles. You know, if you think of these equations in a more exponential form, and you think of this area as a piecewise function, you know, you're looking at it from 0 to 4. It's got a specific relationship on there. Excuse me, we could rewrite that equation, like I said, exponentially, and then integrate its parts, and by subtracting the top one from the bottom one, you can actually get that area, which is a pretty powerful concept when you think about it. And of course, you know, the process of integration is a little tricky at first. You add 1 to the exponent, and you got to multiply that part by the reciprocal. So the reciprocal of 3/2 would be 2/3. That way these 3's and 2's would cancel out. You'd end up back with 2 again. And again, it's over a piecewise section of the curve of the graph. And I do the same thing here. I'd add 1 to that, multiply the reciprocal. And by taking the 0 and 4 and plugging them in, I can actually get that area. It's a pretty profound concept when you think about it, because it goes all the way back to the basic idea of area equals 1/2 base times height. And eventually, you know, we'll do some of that a little more complicated things with cosine and sine and tangent, things like that. It'll be great. And you'll be jumping out of your seats up and down. Wow, Mr. Hess, how do we do this? I can't believe I learned this on my own at home. I never thought I could do it. Now, I want you to just keep one thing in mind. These specific problems are not on your paper. You've got that little chicken on there. There is a time delay on everything we're doing on here. And this just so happens, it's coincidental really, that the time delay on this one, you know, today for me is April 1st, 2020. And, you know, an honor student earlier this year gave me this idea to try to ridicule you a little bit and mess with you a little bit. So, April Fools, thank you very much. Come back in a moment for part 2. It's going to be very exhilarating. We'll talk about what the heck CPCTC really is. It is not integral calculus. Sorry.